When looking at redox reactions, it's important to note that not only do we have to balance the mass with the reactants and products table, but we also have to balance the charge. We have to keep track of electrons. The idea with redox is that something is using electrons and something is producing electrons, and that number of electrons has to match. With a simple reaction where something's just giving electrons from one thing to the other, you can either add spectator ions and make it balance, or you can kind of look at it and make it balance. But the most common way to do more complicated redox balancing is using the half-reaction method, and it's in pretty much every textbook. And we can extend this a little bit later for basic solutions, as we'll see. But for right now, like, the basic skill we have to have is assigning oxidation numbers. For some things, like things that are ions, it's a 1+ in this case. Copper is a 0 in its elemental state. Copper is a 2+ here. And silver is a 0 in its elemental state. So assigning oxidation numbers, that's what we have to have as a skill going into this. And then you just look and see what's happening. Is it redox? Yes, it is. I've got a 1+ turning into a 0, and I've got a 0 turning into a 2+. 1 is going down, it is reduced, so that's our reduction. And 0 is going up, it is oxidized, so that's our oxidation. And we're going to set those up as two half reactions, so that's the idea. What if I look separately at the thing using the electrons and separately at the thing that is producing the electrons? And if I balance those individually, I can recombine them, kind of using a transitive property. So our oxidation involves the copper turning into copper 2+. We have copper turning into copper 2+, all right? In our reduction half reaction, and we can spot this just by what I look at. 1+ going to 0, whatever is involved with this and this is my reduction. 0 going to 2+, whatever is involved with this and this is our oxidation. So we've got these silver ions turning into elemental silver. We're going to follow these steps right here. For a problem like this, it's trivial, but I want us to get the process set up before we actually apply it to more complicated problems. So the first thing is assign the oxidation numbers. We did it. We split it into half reactions based on what those numbers were. We're going to balance everything that's not hydrogen or oxygen, and we'll talk more about that in a minute. But for right now, 1 copper, there's our mass balance for copper. 1 silver, there's our mass balance for silver. That looks good, all right? Then we're going to take care of any oxygens using water, okay? I don't have any oxygens here. I don't have any oxygens here. It's no big deal. I don't have any oxygens here. I don't have any oxygens here. It's no big deal. And so this seems weird because we've never done anything like it before in regular mass balancing for traditional types of reactions. But something to consider with electrochemistry is there are other things there in the solution. In fact, if it's an aqueous solution, you have water. In fact, you have plenty of water. So what we're going to do is we're going to keep track of our oxygens and balance them out using the water. And then we'll keep track of our hydrogen ions by putting it into an acidic or a basic solution. And this only says H+ for right now, but we'll deal with that later when we get to basic solutions. So for right now, I don't have any oxygens, so I don't have to worry about the water. I don't have any hydrogens, so I don't have to worry about the hydrogen ion, and that leaves balancing the charge. And this, I think, as we looked at in the previous video, is where people can sometimes stumble a bit. It's not a big deal in an example like this, but as we get more and more compounds, it'll become an issue. So right here, this side of that chemical reaction, there's no charge right here. The copper is in its elemental state, so the charge on that side is a 0. As we look at this side right here, this is an ion. This side does have a charge, and it's a 2+. All right? It says balance the charge. All right? And we're going to balance that charge using electrons. There's a 0 there, and there's a 2 there. If I add 2 electrons right there, this side becomes 0, and it matches that. They won't always end up 0, but they do have to match. We are using the electrons because that's the basis of oxidation-reduction, is the transfer of electrons. And we're not taking electrons away over here. We don't say copper minus 2 electrons ends up copper 2+ plus 2 electrons. We're looking at things for chemical equations always in terms of adding. Everything's a plus. So subtracting 2 electrons there would be equivalent to adding 2 electrons there. And it makes sense in the big picture because for an oxidation reaction, we expect to produce electrons, right? And in a reduction reaction, we're supposed to use those electrons, and those electrons have to match. So as we look at our reduction half reaction, we've got 1 plus on this side, we've got 0 on this side. To get them to match, we're going to have to add in 1 electron. So done, done, didn't have to do it, done. And now we need to make our electrons match so that we can recombine and reduce these. So if we look here, 2 electrons and 1 electron, our least common multiple is going to be 2. And this is the part that isn't super intuitive if you look at this. This looks like the mass is balanced because it is. This doesn't imply the charge is balanced. You have a 1 plus and a 0 is 1 plus on that side, and you have a 2 plus and 0, which is a 2 plus on that side. 1 on that side, 2 on that side doesn't work, but this will take care of that for us. So once again, I have 1 electron and I have 2 electrons. I'll fix it by doubling that entire reaction. I cannot emphasize enough how much people forget to distribute. So as lame as it seems, I'm going to distribute that right away. Okay, and that's important when we look at the recombining step, because that's where people really tend to make mistakes. So at this point, when you recombine, we're literally taking everything that is a reactant, and it's a reactant now, and we're taking everything that is a product, and it is a product now, as we recombine for one chemical equation. So I've got copper, and I've got 2 electrons, and I've got 2 silver ions, right? And that's going to give me copper ions and 2 electrons and 2 silver ions. I would compare this a little bit to like a transitive property or something. It's not written with pluses, but if you think about it, the commonality between these 2 half reactions is the electrons. So if this stuff is related to 2 electrons and this stuff is related to 2 electrons, then this stuff is related to this stuff. And so that's why the electrons have to match. And if the electrons don't match in this step, then something went wrong and you need to go back and fix it. So I've got a 2 here and a 2 here. That looks okay. Done, done. And what I have left is the actual reaction. There's nothing else we can reduce. So there is the potential to reduce other things. Doesn't come up in this example. Then you'd write it with your phases back in. And you could carry the phases all the way through, but that's a lot of writing. And our redox equations are nothing if enough writing already. All right, so then there's our 2 silver solid for that, and there's our balanced redox equation. Again, this one's trivial because you could have just looked at it and said, oh, I'm going to need 2 of those so that that'll balance out, but it's the same process. All right, so we'll take a look next at a slightly harder example, but we're going to use the same process, so it won't be terribly foreign to us. We're going to take a look at tin metal reacting with the permanganate polyatomic ion. And that's going to give us manganese ions and tin ions. As we look at it, it's worth noting that this one's going to be in an acidic solution. And it's also worth noting that if you tried to balance this by setting up a reactant product table, you couldn't even do it. We've got oxygen on that side, we don't have any oxygen on that side. So that should be a big tip-off that something's going to have to be done differently for balancing this type of reaction. We have to quickly assign our oxidation numbers. In this case, we've got a 0. This is 2 minus, so we get 8 minuses. And that's manganese has to be a 7 plus. Manganese is a 2 plus there, and tin is a 2 plus there. So that's pretty quick in terms of looking for our oxidation numbers. It might help for later, or at least for our answer, if I put the phases in, we'll say that's solid and aqueous, and aqueous, and aqueous. All right. We'll look at what our actual oxidation states are doing. Tin is going to a 2 plus. From 0 to 2 plus is an increase, that's oxidation. And our manganese is going from a 7 to a 2 plus. As it goes down, that's a reduction. And that's how we're going to identify our oxidation and reduction half reactions. Just include the stuff that is associated with whatever's changing, all right? So for our oxidation half reaction, we're going to have the tin turning into the tin 2 plus. And for our reduction half reaction, we're going to have the permanganate turning into manganese 2 ion. All right? So we did it, and we're going to balance everything that's not hydrogen or oxygen. Again, this is a simple example in regard to that. One tin, one manganese, one manganese. We're done with that step. Now we're going to balance oxygens using water, and remember that water is coming from the solution, so we have plenty of it. No oxygen, that one's done for that step. 4 oxygens, so we'll add in 4 waters right there. And immediately you can say to yourself, oh, like I've already messed something else up. Well, the next step takes care of that. In fact, it's kind of a hierarchy of things taking care of themselves, which is fix everything that's not hydrogen or oxygen so that you can fix the oxygens using water so that you can fix the waters using hydrogen. So it works out pretty well that way. I've no hydrogens here. I have 4 times 2 is 8 hydrogen ions there. And we've taken care of that 4th step. The 5th step says we're going to balance charge. And again, I really feel that this is a place where people can go wrong. In fact, I know this is the most common place I've seen people go wrong. Just trying to fix my penmanship there as we go into a scarier step. This right here is a 0. It's in its elemental state, and this is a 2+. We would expect in an oxidation reaction to be producing electrons, and it makes sense that we're going to have to add 2 electrons to cancel out that 2+. As we look at the reduction reaction, the water doesn't have a charge, all right? And the manganese has a 2+, so this whole side is a 2+. As we look at this side, I have 8 of these 1+, and I have 1 of these 1-. So we're going to have overall 7+. All right, so a few things to note. This had a charge, and it had 1 of that charge, so I had 1-. This had a charge, and I had 8 of it, so that was 8+, which combined to give us the 7+. In this case, water had no charge, and I had 4 of them, and manganese had a +2 charge, and I had 1 of them. That's where these things are coming from. To make our to make our charges match, it's going to take 5 electrons right there. 5 and 7 gives us a 2 remaining, and that's a 2+ right there. So this is a half reaction, it is balanced. This is a half reaction, it is balanced, but they don't have this common number of electrons there. And we're going to have to make it match. And the only match we can have here, or at least the least multiple match, is going to be a 10. I need 10 electrons. So I'll have to do 5 times this reaction and 2 times this reaction. I need this number and this number to match. We're going to find a way to do that. So I will distribute it right away so that I don't forget to do it later. That's a really, really important step in my opinion, because it's a very, very common place for people to make mistakes. All right, 2 there, 2 there, 8 there. All right, so we should have 10, 16, 2, 2, 8, 5, 5, and 10. And we're going to recombine. Everything that is a reactant will stay a reactant. Everything that is a product will stay a product. And I know this looks like a mess, but all we have to do is carry it down. So I'll say it doesn't matter which order you go. If you said the hydrogens and the tin and the permanganate and the electrons, doesn't matter. We just need them all. So I've got 5 tin and 10 electrons, 16 hydrogen ions, and 2 permanganates. And that's reacting to give us tin ions, 5 of those, and 10 electrons, 2 manganese, and 8 waters. All right. Sorry, I didn't budget my space very well there. We had warned you previously that, like, if you don't have matching electrons at this point, you did something wrong. Go back and fix it. The next thing we'll look for is, can anything else reduce? Well, tin and tin ions, those aren't going to reduce. Permanganate and manganese aren't going to reduce. Hydrogen ions could reduce if I had any over here, which I do not. And water could reduce if I had any over there, which I do not. So we're just going to carry down and add our phases in. We've got 5 tin and 16 hydrogen ions. And again, those hydrogen ions are coming from our acidic solution. It has surplus of hydrogen ions floating around, 16 hydrogen ions, 2 permanganate ions, and we've got 5 tins, 2 manganese. This is aqueous, by the way. Aqueous. And 8 waters. And the water will be a liquid, and that's how we're using it. So there is our answer for that one. So we'll up the difficulty and then end this video like a half a notch in difficulty. What happens if we have two things, and what happens if we have to combine both hydrogens and waters in reducing at the end. For right now, these examples are just going to be examples in acidic solution. We'll take a look at the examples in basic solution at another point in time. But let's try this right here. The reaction of ethanol, CH3OH, and dichromate, Cr2O7, 2-, and that'll give us formaldehyde, CH2O, and Cr3+. All right, put some phases on there, and we'll declare that is aqueous there. This is still going to be in an acidic solution, and the reason that's going to come into play is when we need to balance our hydrogens right there. We need to get oxidation states, and one of the reasons I wanted to look at this specific example is because something unexpected happens along the way here. We've got 1+ and 1+, that's 3 pluses and 1+. We've got 2-, so there's 2- there. And if we add that up, that's a 4 and a 2, so this carbon has to be a 2- to make that work out. All right. As we look at this one, 2 minuses has to add up to 2-, 14 minuses. We're going to balance that out with 12 pluses, so each of those chromiums has to be a 6+. And this one's a 3+, leaving us with this. So hydrogen's a 1+, oxygen's a 2-. We end up with 2 pluses and 2 minuses. That's got to end up 0, and the only way that can happen is if the carbon's 0. So I think that's kind of an interesting example where you do end up with an oxidation state of 0 in a compound there. All right, I want to erase this because our space is going to be precious here, and I want to look at what's happening. We already said something was happening with that carbon, so there we go. There's an oxidation taking place. It's going from a 2- to a 0. As you look at the chromium, it's going from a 6+ to a 3+, and that is a reduction. And we can breathe a sigh of relief because we needed both an oxidation and a reduction in order for this to be a redox reaction. Let's write our half reactions and see how things go from there. Our reduction is the dichromate turning into the chromium 3+ ion, and our oxidation is the methanol turning into the formaldehyde, or methanal. So as we look at this, first step, balance everything that's not hydrogen or oxygen, I guess I should say. Second step, balance everything that's not hydrogen or oxygen. 2 chromiums here, 1 chromium there. I think that's the first place people go wrong, is very often we don't have to do that step. It doesn't come into play, and when it does, you got to watch for it. So 1 carbon, that looks okay. We're going to balance our oxygen using water. I erase the O again. Balance the oxygen using water. We've got plenty of water around in the solution. So I've got 7 waters there and none here, so I'm going to need, 7 oxygens there. I'm going to need 7 waters over there. As I look at this one, I've got 1 oxygen here and 1 oxygen here, so that won't have to change. The next step says balance hydrogen using hydrogen ions, and those hydrogen ions are coming from our acidic solution. I don't have any hydrogens there. I have 14 of them over here, so I'm going to need all 14 of them to appear over there. Looking at this one, I've got 3 and 1 is 4 hydrogens versus 2, and so we're going to need 2 more hydrogen ions. So did it, balance the charge using electrons. And again, this is like a step that seems trivial once you've had some practice, but until then, it's a step that could cause a lot of problems. This is a 0, all right? I don't care what the hydrogen is, I don't care what the oxygen is, the compound has a charge of 0, so I've got 7 of those zeros. That's not contributing to the charge. I've got 3+ and 2 of those gives me a 6+ on this side. On this side right now, I've got a 1 plus 14 times, that's 14 pluses, and I've got a -2 1 time. So we end up with 12 pluses on that side. Those don't match. I'm going to add some electrons over here to make it match. They don't have to end up 0, they just need to end up the same. And in a reduction, it makes sense that I would be adding electrons, in this case 6 electrons and 12 pluses gives you 6 pluses. Down here, I've got 0 charge on this. I'm not worried about the oxygen individually, or the hydrogen individually, or the carbon individually. I'm worried about the whole thing, which has no charge. I'm worried about the whole thing, which has a 1 plus charge. 2 of them is a 2 plus. This whole thing has no charge, so that's a 0. Okay? I need to make a match, and so it's going to take 2 electrons on this side, and that'll get us a 0. And it's reassuring that our oxidation is producing electrons. And now we need to recombine them. In order to do so, we need our number of electrons to match, and we can do that by just adjusting the second reaction. All right? So setting this up, I need a 2 to become a 6. We'll use a 3. I'm going to go right ahead and distribute that 3 so that it doesn't become a problem when I recombine. All right? You don't have to, but if you don't, you're going to screw it up. All right? Everyone does. But if it's there, it's one fewer thing to screw up. Right at all your reactants, we've got 6 electrons, 14 hydrogen ions, and some dichromate. We also have 3 of those methanols. All right. My space budgeting is spectacular here. I've got 2 chromiums and 7 waters and 3 formaldehydes and 6 hydrogen ions and 6 electrons. The first thing you want to watch for, obviously, is do the electrons cancel. If they don't cancel, you screwed up, go back and fix it. If they do cancel, like in this case, that's at least one reassurance that you can keep going. Are there other things that can cancel here? Well, I've got H pluses, and I have H pluses. So 6 here, 14 there. We're going to simplify. We're going to combine them. Those 6 are going to cancel out 6 of these, and we're going to be left with 8 hydrogen ions. Dichromates and methanols. Don't have any dichromates, don't have any methanols. I have some waters here, but I don't have any waters there, so we won't have to simplify that. So we'll write our answer here, 8 hydrogen ions, right? Those are aqueous, and our dichromate. And methanol gives us 2 chromium ions and 7 waters and 3 of the formaldehyde. That's going to be liquid. We'll make that aqueous, and we'll have everything we need. So those are varying difficulty examples, and we'll have to take a look at some more specific examples and some unique circumstances in another video. But this gives you the basics, following our rules right there, regardless of how difficult they are.